Hello students, this is Dr. Rumsey, and I am here to talk to you about two-way tables. We're looking for relationships and categorical data, two variables, both categorical. So here's some questions we might be asking where we would use two-way tables to answer the question. Should we market BMWs more to men or women? Or is it about the same? Which age group purchases more iPods? And this should be iPads, bring me up to the 70s here. We have age groups and whether or not the person purchased an iPad. Is political affiliation related to gender? If a child's parents both smoke, are they more likely to smoke? Does taking aspirin reduce heart attacks? All of those are categorical variables. We're looking for relationships, so we do something called a two-way table, which we'll see in a moment. In our example, we're going to find out if seeing an ad affects making a purchase. So we surveyed 200 random people leaving a retail outlet. Did they see the ad in the newspaper? Yes or no? Did they make a purchase? Yes or no? And you get an overall distribution of results. Distribution is just a listing of the results and how often they occurred. And we can put this in a table format. And how we do that is we do this two-way table where the rows represent one variable and the columns represent another variable. For this number, 36, it was the people who saw the ad and made a purchase in the previous slide. Here we had 56 people didn't see the ad and didn't make a purchase, for example. And it sort of screams out to us to add up these totals going across and then add up the totals going down. This is 60. And you'll see either way we add it up, we get the 200 people total. And we have different totals for the people who saw the ad and people who didn't see the ad. So in the end, we're going to turn those into percentages and make a fair comparison to them. We'll talk more about that. So the first kind of breakdown we can do is called a joint distribution, where you just find the percentage in each cell. There's cells in the table. The four numbers, the four boxes inside the table where the numbers go are called cells. Okay, so like there's a cell right there, for example. And we had the purchase variable and the ad variable. Let's put the ad variable on the rows and the purchase variable on the columns. And saw the ad, yes, no. Purchase, yes, no. And then what we would do is take our numbers, 36, 84, 24, and 56, and divide them all by 200. And then we'll get percentages, and that will sum to 1. So that's the main idea, dividing by, when you see a joint distribution, you divide by the grand total in each cell. And when we do that, this is what we get, looking a little nicer. And then we get here 60-40 for percentages and 30-70 for percentages, and that will add up to 1. So this just gives us a breakdown, like, okay, 18% of them saw the ad and made a purchase. 28% of them didn't see the ad, didn't make a purchase, for example. It doesn't tell you about the relationship between them. It just tells you about the overall breakdown of them. And we can also do separate marginal distributions. They are out in the margins of the table. we had 60-40 out here, and that was adding up all the people who saw the ad and the people who didn't see the ad. And that's its own distribution. It's sitting out in the margin. It adds up to 1. It's its own distribution. And then you see a 30-70 variable there. 30% made a purchase. 70% didn't purchase. And that's its own distribution as well. So we have 2 marginal distributions. One for the ad by itself, and one for purchase by itself. And you get those by looking out in the margins of the table. That's why putting those numbers in the margins is important. So every two-way table has 2 marginal distributions. Still can't tell the relationship between the variables, but we're still kind of just breaking them down. So now we do want to look for a relationship. So the main way that we do it is to compare the rows or the columns. You could have compared the columns as well. I'm kind of a row person, so I'm using the rows. So what you do is you look at the total in the group, and then you divide the cells in that group by the total in that group. And you make percents that way. It gives you a new distribution. The grand total won't be 1 anymore. The total for the row will be 1, right? 120 over 120 is 1. And then you'll get 24 over, this is 80. 56 over 80, and 80 over 80. And that's another distribution on its own. We call those conditional distributions. So we have 2 conditional distributions. One is for the group that saw the ad, one is for the group who didn't see the ad. And you can see here on the next slide, we're going to find actual percents here. So for those who saw the ad, purchase was 36 over 120, which is 30, and no purchase was 84 over 120, which is 70. And for those who didn't see the ad, you're going to get 24 over 80, which is 30, and 56 over 80, which is 70. Each of these distributions adds up to 1. They're conditional distributions because you have a condition on them. The first one group has the condition that they saw the ad. The second group had the condition that they didn't see the ad. You know they didn't see the ad. That's a condition. And now we're going to compare these groups. Okay, how would we compare them? Well, we're going to look at the numbers that correspond and see if they're the same or not. So we had, in either case, no matter if you saw the ad or not, 30% made a purchase. So seeing the ad didn't do anything. You see that? Seeing the ad didn't do anything because I have the same percentage in each group that saw the ad, whether the same percentage in each group that made a purchase, whether you saw the ad or not. And then 70% did not make a purchase, no matter if you saw the ad or not. So there is no relationship here. Because the conditional distributions are the same. There's no relationship because If there was a relationship, you'd see differences there. The ad would have done something. The ad didn't do anything. So we can say here, ad didn't affect purchase. So there's no relationship. And so that's how we did it. And that was called method 1, comparing the conditional distributions. If they're the same or close to each other, then there's no relationship. And if they're different, then there is a relationship. So we had them exact. And for this class, for exams and things, I'll make sure they're either the exact same or they're really, really different. So close doesn't really come into it because everybody has a different definition of close. There's a method 2 here, and I have decided, I've made the executive decision that we're not going to do that one. We're just going to look at method 1 because that's the one I want you to focus on. Our next example asks the question, does taking aspirin reduce heart attacks? And check my time here. And I think we're going to stop on this and we will pick this up with part 2. This is part 2 of the two-way table podcast. So the question is, does taking aspirin reduce heart attacks? And this is kind of a big table. You've got a group of doctors, 22,071 doctors, and they either took an aspirin every day or took a placebo, which is a fake pill, every day. So the groups we would be comparing as far as their outcomes would be the 2 columns here. And they followed them over a period of time and tried to see what the outcome was. Some had a fatal heart attack, some had a non-fatal heart attack. That was kind of what it was about mainly. And then some people wanted to know about strokes. And then none means not a heart attack or a stroke. And then all is the total at the end. So we have totals running like this. And this is a two-way table because it has rows and columns. It just has 4 rows instead of the 2. We're just dealing with 2 rows and columns here in this class. So I am going to make this table into one with just 2 rows and columns. So I'm going to put all the heart attacks together. And then I will put all the rest of them together. And then I'll compare the aspirin group to the placebo group. And we'll see what happens. So I'm looking at here. I'm looking over here and I'm wondering how many people took aspirin and had some kind of heart attack, fatal or non-fatal. And you put these 2 together. 10 plus 129 is 139. Heart attack and placebo is 26 plus 213, which is 239. No heart attack and aspirin is all of these, and that ends up to be 10898. And then all the people placebo and no heart attack, 10795. And you can see the grand totals there. We could put them in. 11037 on the bottom of column 1. We'll total that up. 11034 placebo. 378 adds up the first row, and then 21693 second row, and the grand total, as we know, is 22071. And it almost looks like you can compare those 2 columns right off the bat, and you almost can because the totals are so close. When the doctors divided themselves up, they did a really nice job of doing it. And it might look like there's not a huge difference going on, but 139 is different from 239. And I'll explain what I mean in a little bit. So if we compare the conditionals, that's what we would do in method 1. We compare those two columns. Let's find those conditionals and write them down. So for the aspirin group, you have heart attack, no heart attack. It's 139 and 10898 is what you get from that column, but then you're going to divide by their total for the aspirin group, and that's 11037. That's the difference with a conditional distribution, is you're dividing by the total in the column or in the row. The total for that group, basically. So you get 0126 and 9874 there. And then for the placebo group, and that adds up to 1, by the way. And for the placebo group, heart attack, no heart attack, you have 239 over that total for this group, 11034, and 10795 over 11034. And that ends up to be 0.0217 versus 9783. And of course that adds up to 1. There might be a little round off there, but we're not going to worry about that. And now we would compare, right? Compare the groups. So I would compare the percentage of the aspirin group that had a heart attack to the percentage of the placebo group that had a heart attack. And you might say, oh, they're not much different. They're both small. Well, they're both small. But if you take the fact that they're both small, one is almost twice as big as the other. So it looks like aspirin is having an effect here, because the placebo group had almost twice as many heart attacks as the aspirin group. Now, they're both small, but that still counts. And we will show you how you can make a statistic to show how much different they really are. So what we're going to do here is we're going to do something called the percentage difference. So we're going to take 0126, the first number, minus 0217, and we're going to see how different they really are. So we're going to compare it to the original number, 0.0126. So you have the difference between them in terms of the first number. So that keeps the magnitude sort of in mind. So it's first number minus second number over first number. And we're going to get negative 72.22%. So what does that mean? The difference between these is a negative number. That's how much less likely you are to have a heart attack on aspirin. And I know on the aspirin, I'm comparing it to the aspirin because that's what's in the bottom here. So you are 72.22% less likely to have a heart attack on aspirin. And you hear this kind of stuff in the media all the time. You're 100% more likely to have this if you do this, or you have a 10 times greater chance of this if you do this, or if you don't do this. Well, the numbers originally might be very small. The risk might be very small. So even if it's 10 times higher now, it doesn't mean it's all that bad necessarily. You have to put it into context. When you do this percentage difference, the magnitude goes away. What goes away is the fact that both of these numbers are very small. So the 72.22% might seem a little misleading, but it is true. And you have to realize, asking what were the numbers to begin with? What are the risks to begin with? So somebody could say, if you have the surgery, you're 5 times more likely to have a heart attack. Okay, what is my risk of having a heart attack to begin with? And that's what you need to know. And you'll hear this thing in the media all the time. You just have to be aware of it. I'm not going to do method 2, and you don't have to worry about it either. Here is an example of 3 conditional distributions in a table. This is not a regular two-way table because it doesn't sum to 1. In fact, each row sums to 1 or 100%. So it's telling you that this is a distribution since it sums to 1. This is a distribution since it sums to 1. This is a distribution since it sums to 1. So not all tables that have rows and columns are two-way tables the way we're working with them. So what this is saying is for the US, you have a distribution of Facebook and not Facebook of 56 versus 44. Oh, I'm sorry, this should be females versus males. It is all Facebook. Sorry. See these 2 groups here? That's who I'm comparing. All right, so this is 100. For South Korea, and this is old data, so I'm not sure. I mean, I really highly think it's not the same right now, but 44% females and 56% males. The one I'm questioning is China here. 19% females and 81% males. So somebody might want to do some research on that and see if that's still how it is. I kind of doubt it. This is old data. But these are 3 conditional distributions here. Conditional distribution of gender, given they're in the US. Conditional distribution of gender, given they're in South Korea. Conditional distribution of gender, given they're in China. And you can compare those and definitely see there is a relationship between country and gender. There is a relationship between country and gender. And why is there a relationship? Because these percentages are different as you hop across. The percentage of females is different in each country, very different in China, and the males have the same kind of patterns. Okay, I'm going to stop here, and I am here to talk about part 3 of two-way tables. Just as we were learning about two-way tables and how to find relationships, look for relationships, we think we know everything about them. And there's not that much really to tell, but there's a problem. And I want to show you an example of this problem. If we oversimplify two-way tables, we might get ourselves into a little bit of trouble. And more importantly, when you're looking at other people's two-way tables, they might be getting into some trouble and you need to spot it. So here's the example. Which hospital is safer, A or B? Well, that's a hard question to answer when you're looking at the word safer. What does that mean? So first you have to define that. So what these people did who collected the data was they broke down patient outcomes for each hospital, and they used surgery patients, and they just marked it as died and survived. So it's a pretty simple way of doing it. I don't know if it really shows one hospital is safer or not, but that's one way to do it. So they broke down patient outcomes for each hospital, A and B, and they compared the conditional distributions, and then they decided. Here's the data in a two-way table. There were 2,900 patients. You have hospital A versus hospital B, so I'll circle those columns there. 2,100 people in hospital A, 800 people in hospital B. And what are we going to do with this information? Well, first, we can look at the marginal distributions of hospital and outcome. Those are our two variables. If we look at the marginal distribution for hospital, we can say hospital A had 2,100 patients over 2,800 or 2,900, and that is 72.4% of the patients. And hospital B had 800 over 2,900 patients, and that was 27.6%, which adds up to 100%. That's the marginal distribution for hospital. If anyone asks you to find that, that's how you do it. Take those numbers and divide by the grand total for marginals. Now, outcome, you have died, survived, and we look for the total number that died, 79 out of the grand total, 2,900, which is 2.7%. That's the overall death rate, okay? Keep that, we might need it later. 2821 over 2,900 for survived, which is 97.3%. And that adds up to 100%. So we have two marginal distributions here. It just gives you a rough idea. A lot more patients going to hospital A and not very many deaths, which is a good thing. Now, the conditional distributions, we would be comparing hospital A and hospital B in terms of the outcomes. So we would say for hospital A, you have died, survived, and the ones that died for hospital A, 63 out of 2,100 is 3%, and of course the survivals have to be 97%. We're really mostly interested in the death rates here. For hospital B, we have died, survived, and they only had 16 deaths, but they only had 800 people too. That was 2%. And then survival has to be 98%. So conclusion at this point is hospital B appears to be safer according to their definitions. So I'll put little quotes around that because it has a lower death rate. Okay. But that's not the end of the story. If we were just doing a two-way table, we might think that's it. But hospital A doesn't want to go down without a fight. So they're going to say, wait a minute. You're not accounting for some of the other issues that are really, really important in this data set. So what could hospital A be thinking about? What's happening to hospital A to sort of bring up the death rate, but still makes it do a good job? In fact, better than B. Well, we're going to look at the condition of the patient. There's other variables you could think of too. This one's easy to get a hold of, though, in terms of collecting data, going back and looking at the data. What was the condition of the patient before they went into the hospital? Hospital A is kind of trying to say, well, I think we're getting more people in bad shape. Let's see if that's true. So now we have two-way tables. You could call this a three-way table if you stack them up. We're looking at three variables. We're looking at condition of the patient. We're looking at which hospital. And we're looking at the outcome. All right? And there are some totals here that are interesting. On the left, in the good condition patients, you have just as many from hospital A as hospital B. But in the poor condition patients, you have 1,500 going to A and only 200 going to B. Now, what's the problem with that? Well, what do you expect the death rate to be with poor condition patients? Higher, right? They had 65 deaths out of 1,700, as opposed to 14 deaths out of 1,200. So how do we sort of dig up the statistics that we need to show this? So far, we're kind of thinking hospital A did better than hospital B for each group separately. Hospital B did better than hospital A when you put them all together. And how is this possible? Now, this I didn't show you yet. Hospital A turns out to do better than hospital B for each group. Let's see if we can show that. Hospital A, for the good condition patients, has a death rate of 6 over 600, which is 1%. Hospital B's death rate is 8 over 600, which is a little higher. Granted, it's not a lot higher, but it is higher. So A's doing better, and guess what? Same thing happens over here. Poor condition patients. A has 57 deaths out of 1,500, which is 3.8%. Of course, it's going to be higher because you have poor condition patients. And B turns out to be 4%, taking 8 over 200. So again, A is doing better. So A did better when you looked at the condition of the patient in both situations. But when you put everybody together, A looks worse. That's called Simpson's paradox. How is this possible? It's called Simpson's paradox. And here are the actual percents. You can see what I was working on, the 1% death rate for hospital A in the good condition patients versus 1.33, 3.8 versus 4 there for the poor condition patients. And the magic numbers here are 1.17 for the overall death rate for good patients, 3.82 for the bad patients. So hospital A is getting a ton more of the poor condition patients, and they have a higher death rate. They're only getting 50% of the good condition patients with the lower death rate. So that's what's going on here. It's a weighting system. W-E-I-G-H-T-I-N-G. There are more patients in poor condition also, and more patients in poor condition going to hospital A. The death rate of patients in poor condition is higher overall. Let's look at this. There are more patients in poor condition. Let's go back. 1,700 patients in poor condition versus 1,200. So it's important to be able to read tables, pick out the numbers that you need that make the case that you want to make. And you'll probably be in this situation sometime in your career. So think about other variables, get other data, look at things in different ways. This is called Simpson's paradox, when in a two-way table, you get certain results, and those results reverse that's funny. Those results reverse when looking at three variables. So you've got this third kind of confounding variable out there that's messing up the original results, but is more realistic if you think about it. So break down results further, not just by one variable. Look for these confounding variables or lurking variables. They're variables that weren't accounted for first in the first round, but they do affect the results. Look for those variables and collect data on them also. Which is the most informed data set? The one is further broken down to a point. I mean, you don't want to go with a 19-way table. It gets crazy after a certain point. This is a common phenomenon in the real world. It doesn't happen all the time, but it happens a lot. So be careful when you're looking just at two-way tables, especially in election years, when there's a lot of data floating around. Look for that kind of stuff. That's the end of our two-way table discussion. Thanks for listening.